Okay, Q2B5 is an example of a two-slit interference experiment. And so what that looks like is I have a slit here and a slit here. And I have a central axis here, and I'm really far away, and I have a screen that's here. The separation between my slits here is little d. And so this is from the center of this slit to the center of this slit is little d. Now what I have on my screen here is I have a maximum here like that. And as I go down the screen or up the screen, I end up with adjacent maxima that look like this. And so what they're asking us to find is they want us to find this this distance here. This, we'll call it S. The distance on this screen between this first maxima and the central maxima, the 0th order and the 1st order of these, we'll call them diffraction spots. Okay, and so we needed to find an angle from the center of our slits to this first maxima, and we'll call this theta. And so the other thing we know is we know that the screen is a distance d away, and that's 3.2 meters. Okay, so let's look at this for a minute. I can see here that if tangent theta is equal to, so I have this is my triangle here, is equal to opposite over opposite over adjacent. So it's opposite over adjacent, so it's going to be S over D. And I also know that for small theta, and that's about less than like 1 degree, I know that theta is about equal to tan theta, and that's about equal to sine theta. So for really small angles, I can approximate tan theta for theta and sine theta for theta. Okay, and so now for this two-slit interference experiment, I need to use the equation d sine theta is equal to n lambda. And what n here is for this central maximum, n is equal to 0. But for the first maxima here, n is equal to 1. For the first maxima below, n is equal to -1. For the second maxima, n would equal 2. And for this one, n would equal -2. So these are the orders. So this would be the 0th order, 1st order, 2nd order, 1st order, 2nd order, where n above the axis is positive and below the axis is negative. All right, so now I can plug in here. I have sine theta, and I know that this angle is really, really small because I'm really far away from my slits here. So I know that theta is about equal to tan theta, which is about equal to sine theta. So then I know that d sine theta, I'm going to substitute theta, is equal to, I now just have lambda because I know I'm using n equals 1. Now I also know that theta is about equal to S over D, this tan theta. So I'm going to plug that in. So I have D is equal to, or D times S over capital D is equal to lambda. And now S is what I'm looking for. That's what I'm solving for here, the spacing between adjacent bright spots. So I'm looking for S. So if I multiply both sides by capital D and I divide both sides by little d, I'll end up getting S alone. So I have S is equal to lambda capital D over little d, and I plug in numbers here, and I have 633 times 10 to the minus 9, right? That's what nanometers are up here, meters. And D is equal to 3.2 meters, the distance from the slits to the screen, and then little d is equal to 0.04 millimeters, so that's going to be 0.00004 meters. And that equals, when I plug it in, I get 0.051 meters, or S is equal to 5.1 centimeters. So that's this distance here is 5.1 centimeters on a screen that's 3.2 meters away.